Yes.
Hey, next,
So
you have Discord on this laptop, right?
I have Discord in the no.
Not.
No, why?
How do you share this meeting?
All right.
I'm not.
I want to talk about final exam for a couple minutes. Okay. So final would be only on the material, plane wave, lossy medium, normal incident, and transmission line. And there would be 3 or 4 problems only on these topics. Right. And most of the time we spend on is the wave. So that means the majority of your exam would be on the wave part. You should know how to write EM wave, right? E field, H field, under any conditions, under normal incident, any polarization, lossy medium, right? In fact, I can just put one problem and combine everything in one problem. If we have time, I want to do an example like that. Okay. Now, to prepare for the exam, if you haven't been doing so, number one is go over the examples we did in class, because that's the most fundamental, most basic things I want to learn. I want you to learn. And if you did not even learn that, forget about doing any problem because you won't be able to, right? Number 2 is do the problems for my book, because the other book, we did not share that chapter. They do have a chapter on normal incidents and the lossy medium is in your chapter. But if you can do the problems in my book, you should be able to do the problems in the regular textbook, right? For the problems that I have not even talked about in class, that means I'm not going to ask you questions in the exam. Fair enough? Okay, so you need to know what I have been talking about in class, right? Okay, any questions?
Did you post ask a key for?
No, I won't. But if you're, I won't, because otherwise people would be, you have the problem, people have solution of all my homework problems, which are all exam problems. Did that help them to do the exam? No, because people just used to get 99% in the homework and get like 10% in the exam. You explain to me why. Because they have the solution. If you already know the solution, you're not going to learn. I guarantee you. Right? We learn by struggling. A lot of the stuff that I talk about in the class are the problems I struggled when I was a freshman, when I was a sophomore. I'm serious, because those stuck with me. Those I learned. Right? Problems that I have not been giving a lot of thoughts about it. Even though I took it for granted and did well in the exam, I didn't learn anything.
Well, just to answer without.
But what I would encourage you to do is to share your answer with the class on Discord. Hey, I did this problem. This is my answer. What do you think? Do you guys get the same answer? Right? And then start a discussion. People will say, no, I don't. I get this. And then that's how you learn. Troubleshoot and learn it. Right? Okay. I'll share the one last time. Okay. And he has all the solution because he did all the problem by himself. He has not looked at my solution at all. Right?
Which means they could be wrong.
No, I look at a lot of them, right? So there are only 10 problems in each chapter. And you can pretty much skip chapter 7 if you already know how to do the EM wave. Because if you don't know chapter 7, you will not be able to do any problems in chapter 8, the lossy medium and the normal incident. So if you can focus on those 2 chapters, 20 problems, if you honestly understand them, not knowing the answer. Again, if you work with a group and other people present you the answer, and you think you learned it, you didn't, right? You didn't. If you didn't do it yourself, you didn't know. You don't have to do all 20 problems, but if you have a good percentage, like half of them, I can do it on my own, that is a good signal that you're walking in with confidence, right? If you say, oh, I can do that after I talk to my TA every time, that means you cannot do the problems on your own. right? You don't fool yourself. Don't fool yourself. You cannot fool yourself. You know it. When you walk, before you walk to the room, you already know how much you know and how much you don't know, right? When people go to Olympics, they already know what they can do, what they cannot do. It's not like, I think I'll test my luck today. No such thing. All right, good enough for final? Okay. I cannot share. Yes, I can. Why not? Come it's not share.
I think it might be. Yeah, you should be. Just alt tab.
What?
Just open that window.
Just go to the top right. The little line.
Minimize the window.
Yeah, that one. That's it. You
Am I sharing?
should be.
Looks.
Okay. All right. So let me recap what we have done in transmission. So the first formula we derived to is this one, right? Gamma. What is gamma? Reflection coefficients. What does that tell you? How much electric field amplitude is going to be reflected? This is exactly like what we have done in the electromagnetic wave. I have a wave going in, hit the boundary, coming back. How much of this amplitude of the electric field is being reflected, right? But that's for calculation, that's what it is. But in practice, this is a very important formula. What does that really tell me? Number one, what does that mean by characteristics impedance, right? Because again, when we say the system is 50 ohms, we cannot measure the 50 ohms. We cannot use the ohm meter to measure 50 ohms. So what does that mean by 50 ohm system? That's what it means. When I inject the signal, right, connected to a 50 ohm system, I have no reflections. That's what it means. More important, because that's exactly what we measure. Because we cannot measure impedance. Characteristic impedance, we cannot measure. We cannot even measure voltage and current at high frequency, right? I mean, think about it. If I'm at 12 gigahertz, what instrument do I use to measure voltage? Our digital meter doesn't go that fast, right? So the only thing we can measure is I know how much power I'm sending in. I can measure how much power being reflected or transmitted. Right? The gamma and the taus are the ones that we can measure, the reflected power and transmitted power. That's why I emphasize on that concept, gamma squared, 1 minus gamma squared. And you need to know that well. Okay. The other thing is, if I write it normalized or not, I mean, sometimes I write it this way because it looks simpler. So most of the exercise is I give you the impedance, right? The impedance of the load. When we say the load, it means the impedance of whatever I'm going to connect to my transmission line. It could be a radio, it could be an antenna, it could be a filter, it could be an amplifier, whatever I'm looking in, right? That's the low impedance. What we're saying is, if I present you with a low impedance, a low, then you can tell me how much reflection I'm expecting to get. But more likely is the other way around, is when we measure the reflections, then I can determine what's the low impedance. So from this, you can do an algebra. If I know C, I can find gamma, but if I know gamma, I can also find C, right? Those are simple algebra. You should be able to do it. Don't say, oh, you don't provide that in my cheat sheet. You won't get that, right? The next formula, we don't have a lot of formulas in this chapter, but the next one is this normalized or unnormalized. Again, this is a very important formula, and you need to know how to apply it at different places. This tells me if I'm connecting a load, again, whatever I connect to the transmission line is the load. Then I can tell after the transmission line what is the impedance, right? Because the impedance is not constant. The only time the impedance is constant is when everything is matched to 50 ohms, the same common system impedance. So if I design a unit that is 50 ohms, that means when I connect my cable to it, the cable will see a 50 ohms. And if my cable is 50 ohms, which is all the test cable you can buy in a communication lab, 50 ohms. So when the characteristics impedance is 50 ohm, when the low impedance is 50 ohm, then all this is equal to 1, right? And then in that case, your impedance of the input is always the impedance of whatever you connect to, right? So all the transmission line that you are not really using for design, you can guarantee they're all 50 ohm lines, even internally, because then I don't have to worry about the length of the line. I can route it to whatever I want to route to, just like, on the low frequency circuit board, right? Questions? So let's talk about standing wave. Right. So remember what standing wave is. If you have two waves traveling in the opposite direction, but with the same frequency, same medium, same wavelength, then when you add them together, it becomes a standing wave. Right? A typical, when we first learn it, a typical standing wave looks like this, right? But what does that really mean? It means at one time you will see the wave to be like this. At a later time, it might have an amplitude like this. At some time, it might have an amplitude just flat. At some time, it will be. So it's always bound by this envelope. We're not saying the wave is always going to look like that. Only if we average it over time, because we cannot see it so fast. Our eye is not so fast. Our instrument is not so fast, right? When you hit the guitar string, if you shine a light and really look at it, you see a standing wave ratio, a standing wave pattern. It will be looking like this because our eyes cannot follow the string at any real time. We can only see the average, right? And that's what it really means. Are we okay? Okay. So now we are saying, again, what's not showing is I have a function generator sending a wave here, and then the wave traveling into the transmission line, see a low, a different impedance, it reflects, right? And then this incoming wave plus the reflected wave, the V plus and the V minus, together will form a standing wave. And in an ideal case, how do we define a standing wave? Is over time, there are certain locations where there's no displacement, there's no change. We call those the nodes, right? The amplitude is always zero, as if it doesn't move at all, right? Remember, you must have seen it, people excite a plate and then put salt on the plate and you see a very nice pattern. Nice pattern, right? The salt are sitting at the node. So how do we get this node? Is at any time the forward wave would cancel the reflection exactly. And the amplitude would be exactly the same all the time. So one is plus, one is minus, so at this point, it's always zero amplitude, right? Make sense? However, in our case, the refractions depends on the impedance here. It's not always carry the same amplitude going back, right? Unless you have an open or short circuit where everything is going to reflect. Otherwise, your refraction usually has a smaller amplitude, right? Which means at the node, there's no complete perfect cancellation, right? The V plus is always greater than V minus, but it's still form of standing wave, but the standing wave would look more like this, with some maximum, some minimum, some maximum, some minimum. So this is more realistic standing wave, okay? And we are going to find out not really exactly the maximum and minimum, but the ratio of it. The ratio of the maximum over the ratio of the minimum is what we call the voltage standing wave ratio. We're going to talk about that. Okay. All right. So here we go. Now it's the math time. So we say the voltage is a wave, has a forward wave, has a reflected wave going backward, right? This part you all understand, right? And now if I want to find the magnitude of this voltage wave, again, because I cannot follow everything in real time, I can only look at the average magnitude. So if I want to find the magnitude of this, first of all, I can rewrite this. Gamma low is defined as V naught minus over V naught plus, right? The reflection amplitude right at the low. So I can just rewrite it, make it look a little bit nicer, and then find the amplitude of it. The amplitude of this is the amplitude of, the magnitude is the amplitude of this, which usually is a real number. And then the magnitude of this is just 1 because this is a phasor, just a phase. E to the I, E to the J, theta, the magnitude is always 1, right? And then the magnitude of this, right? So far, so good? Okay. I'm going to just skim through the derivation. You should try to fill in all the steps yourself, right? Especially if you think your math skill is deteriorating or your math skill was never good enough, you should take this opportunity to, try to refresh it and make yourself better. If you would skip all this opportunity to use the math, pretty soon you won't be able to do any when you need it. Okay. All right. So I'm just going to highlight this. So this is just the amplitude. Gamma can be a complex number. We've seen that in electromagnetic wave, right? So I'm going to define 3 lines means defined by. I'm going to define the gamma low has a magnitude of rho, have a phase angle of theta. We just define it. The magnitude of reflection coefficients, rho. The phase angle, theta. So if I put this in here, then I can write rho and the phase angle absorbed in here, right? So far, so good. This amplitude usually is a real number, so we assume it is and just take it out. And then now, how do I find the magnitude of a complex number? This is a complex number, right? How do I find the magnitude of a complex number? The square root of the real square plus the imaginary square. What is the real part of this? 1 plus rho cosine of this phase angle. That's the real part. What's the imaginary? Is rho times the sine of this, that's the imaginary. So this is real square plus imaginary square, right? And then you expand the square, and cosine square plus sine square is equal to 1. You use that property and you reorder it. Now you have 1 plus 2 times this plus rho square. And now you want to do the complete the square exercise you learn in middle school or high school, right? And then you complete the square, subtract the extra term out here. And that's what you end up getting. And this one, 1 minus cosine theta is like 2 times sine square half theta formula, right? Trigonometry. Go back and review it. And so you get to this. So now what? Now I can define the maximum and minimum. This is the amplitude, the magnitude of the voltage as a function of position at any point in the transmission line. Where do I find the maximum? The maximum is when I'm subtracting these 2 numbers. The maximum of this number is when this one is 0, right? Right? When this is 0, then my maximum is the square root of 1 plus rho square. That's just equal to 1 plus rho. So the maximum of the voltage is the V naught plus 1 plus rho, right? When this is equal to 0. When do I find the minimum? The minimum is when sine square is equal to 1, right? Then I'm subtracting the maximum number, which is 4 rho, right? And so my number would be 1 minus rho square minus 4 rho. Now you expand this and that becomes 1 minus rho square. You take a square root, that's what you. Okay. Simple algebra, fill in the step yourself. This is the V plus voltage maximum. This is the voltage minimum. Now I take the ratio of them. It's called the voltage standing wave ratio. I didn't take it. I took it in the next page. Let me do that first. Why not? Right. What is this ratio? Well, the maximum, this is a maximum, this is a minimum. So the maximum over the minimum, 1 plus rho over 1 minus rho. What is rho again? Rho is the magnitude of the gamma. What gamma are we talking about? The gamma, the refraction that make up of this standing wave. So if this is a transmission line, this is a forward wave, it's this gamma, this refraction that would create a standing wave here. Are you with me? Okay. In the problem, we might have like multiple transmission line, multiple components, you know, whatever components I have. So if I'm looking at the standing wave in this transmission line, I need to find the gamma in here, not the gamma in here, right? There are multiple gamma, there are multiple reflections in the problem, in the circuit. Every time you have a new impedance change, there's going to be reflections, right? You need to know which reflections would create a standing wave in this transmission line. I'll do an example at the end, or maybe next time, right? I'll do examples. Okay. Yes.
Since there's another impedance farther down in that area you're looking at, wouldn't you have the reflection from the far end as well?
Yes.
So you have to imply it down.
Okay, so the question was, wait a minute, here I have a reflections here too, so shouldn't I also include this into my reflections, right? The answer is yes, but you don't need to do it. What you do is, when you calculate these reflections, you don't calculate the reflections between these two transmission lines. You need to simplify this circuit altogether and call this a load. And then you connect that to this transmission line. Then this reflection would include everything to the right side of that point. Okay, so it's included. Good question, very good question. I mean, a related question would be, remember we talked about quarter wave, right? So let's say I have, was it 61 ohm or 67 one? I don't remember. So I have a 100 ohms here. And my system impedance is 50 ohms. But we're saying with this quarter wave, then there's no reflection. Now looking in here as if I'm looking at a 50 ohms load, right? So how does that work? How does that even work? This is how it works. Just like the thin film interference, right? So I have a 50 ohm system sending a 50 ohms wave in my standard transmission line, going in here, seeing a 61 ohms with a transmission line, right, and the 100 ohms. So I have reflections here, right? Some of them would go through reflection and transmission. Now this transmitted wave, seeing 100 ohms, will also reflect, right? Are you with me? So by the time it come back here, I have two waves going out. But what is the characteristics of the impedance? If we choose the impedance correctly, these two amplitude would be the same. And the phase, this is quarter wave. Quarter wave is how many degrees in electrical length? Divided by 360 divided by 4. What is quarter wave again? 90 degrees. So this wave has to travel 90 degrees here, seeing 100 ohms, reflect and then travel another 90 degrees out here. So what's the total path length? 180. That means these two are 180 degrees out of phase. What is 180 degrees out of phase means? One is plus, one is minus. So coming out here, no reflection, as if the whole thing is just a 50 ohm load. That's how it works. That's how it works, right?
Is there not another reflection when it comes back the other way? Like from 60 to 50? Yeah.
You could. So again, this is like the multi-reflection problem. When you come into here and then go into here, would these two also cancel? Right? Right? Okay. Okay. All right, so let's go back to the standing wave ratio. So again, we say the standing wave ratio is 1 plus rho, 1 minus rho, right? And why is that important? VSWR is one of the important spec in the in any RF components. When you buy antenna, buy a radio, buy a they would tell you what's the VSWR, right? Or at least in the older days. Okay, so that if you ever go into interview in something with high frequency, circuit RF company product, this is one of the things that you want to remember walking into the interview, right? Things like what is a dB, what is dBm, what is a VSWR, that kind of questions. You really need to know. If you don't even know this, you have no business in wave, in electromagnetic wave. Okay. So what does that tell me though? VSWR again is related to gamma, right? To gamma, the reflections. So let's take a few special cases. When we have a perfect match, everything is matched to 50 ohms. What is gamma? 0, because 50 ohm means no reflections, right? So if gamma is 0, rho is 0, now you have 1/1, VSWR is equal to 1. 1.0 is the most ideal system that you want, right? And it's never go below 1.1. Again, if you do a calculation, you come up with like 0.7 and you just leave that as the answer. That's a double jeopardy, because not only your calculation is wrong, you also are telling me you don't know what VSWR is. I just plug in the number. VSWR cannot be greater than 1, because this is by definition, right? Okay. Huh? Cannot be lower than 1. Has to be greater than 1. Cannot be a negative number. Cannot be a complex number, right? You have to understand what that number means. The second cases is open and short. If you have an open or short circuit, what happened? You have 100% reflection, total reflection, right? That means the magnitude of gamma is equal to 1. Now you have 1 minus 1 in the denominator. What is that equal to? Undefined. VSWR now is undefined, something over 0, right? So that would be the worst case. When we say the worst case, that means, we want to deliver power to the load, but nothing go in there. Everything be flat, right? So the bigger the number, VSWR, the less power you're going to be able to deliver, right? As an RF engineer, you want to get close to 1.0 as possible.
Can you draw what that would look like? What a standing wave ratio of 1 would look like?
Yeah, I will later. I'll show you a cartoon. So what is so 1.0 is ideal, but the most common spec you see probably about 1.1 to 2.0. Anything above 2.0, that's really bad already. That means you're losing most of the power, right? It's not worth making. No one's going to buy it. Anything below 1.1, like between 1.0 and 1.1, of course, is more desirable, but that comes with cost, is money talk. For example, if you want to buy a 10 ohms resistor, how close to 10 ohms do you want? Is that 10.00 ohms? Or is 9.9 good enough? Or 9.5 is good enough? Right? That is the question. If you go to DigiKey and buy a 10 ohm resistor, probably plus or minus 10%, like either 9 ohms to 11 ohms, you say, yeah, that probably is good enough. But if your system require more accurate resistor, then you need to pay more. You can get something closer to 10 ohms. You can say plus or minus 1% is what I want. Then you pay more because someone has to screen that for you. You can say, I want 10.0 ohms. Yeah, you can do that, and people will screen for you, but are you willing to pay thousands of dollars for one resistor? You probably won't. So, right, you need to justify the cost. So most common is pretty much within this range. These are more not for the final exam question, but more for interview questions. If you ever want an interview, sometimes students will email me, hey, I got an interview, what should I prepare? These are the things that you should review, right? All right. So let's go back one more slide. So we say, this was the equation we look at, and we say, well, if we want a minimum, we want a maximum of this, then we want this to be 0. That means we want sine of this function to be 0. That means we want this angle to be plus or minus n pi, where n is the integer, right? So this is the formula we need to derive, and then we want to solve for x. So I write x is equal to this. Remember, x is equal to 0 at this end, and any point here, x is a negative number. You want to make sure x is always negative. Don't give me a positive number. Always a negative number. Okay, remember that. I will show you how to use this formula effectively and easily, because looking at this is not an easy formula to use. I'll show you how to use it very easy. Right, just follow me. Okay. And then minimum is when this is equal to 1. So when sine square is equal to 1, that means sine is equal to 1, that means it's a 90 degree, right? Minus 90 degree and 3 pi over 2. So it's 2n plus 1 over 2 times pi, plus or minus. So again, we solve for x, and we write this is a negative number. This looks complicated, but it's really not that bad. I'll show you how to use it very soon. Any questions so far? All right. One more thing. If we take the log base 10 of rho, which is the reflection, the magnitude of gamma, multiplied by 20, we call this the return loss. So, right? So the idea is I have a device here, I send a wave signal, and then it reflects. If I don't get everything back, then I have a return loss. It's always a negative number, so a lot of times we put a negative in here, so my return loss becomes a positive number. A lot of working engineers still like to put the negative when they say, oh, the return loss is minus 15 dB. What it really means is return loss is 15 dB, right? But it doesn't matter. Some people just never really get the definition straight. Okay. So what does that tell me? Again, this is the function of the gamma. Return loss is just another way to say gamma, but in dB scale. Return loss is just the reflection coefficient, the magnitude of gamma in dB scale, right? By the way, the magnitude, remember gamma is a complex number. So the magnitude, you know how to find the magnitude of a complex number, right? So when we say gamma square is the reflected power. This is the magnitude square, not this gamma square. They are not the same, and you need to know the difference. In the exams, I see a lot of people do this. Right? You need to know, understand, and know the difference. Right? Okay. So why do we talk about return loss? So remember what VSWR is. VSWR is 1 plus rho over 1 minus rho. So again, it's really related the reflection gamma to me, right? When people say VSWR is 1.1, that means it tells me what rho is, what's the reflection is. That will in turn tells me what the gamma is, the impedance is. Here is telling me the same thing. When I tell you return loss is 20 dB, then you can calculate what rho is, then you in turn can calculate the impedance, right? These two are really saying the same, giving you the same information. So now it's more common to put the return loss in the spec than the VSWR. This is perhaps a little bit older, but there are still components, there are still specification like to quote this VSWR. So as an engineer, you need to know these two both. They both are telling you the same information, and you need to know how to extract that information from these two numbers. Is that clear? Okay. So their homework on my, I think in the standard textbook and also in my book to ask you to do something similar, and you should go through that, right? Just mostly algebra. All right, so what is the typical return loss number? When we have a perfect match, gamma reflection is 0, then VSWR is 1.0, most ideal. But when I have a 0 here, the log of 0 is negative infinity, undefined. So return loss is a huge number, right? Which is not good. But it's good. It's a negative, like really big number, which is good. In dB, I forgot to put dB here. Return loss must be a dB. So when you write a return loss, it has to have a dB at the end. When you have an open or short circuit, total reflection rho is equal to 1. VSWR is undefined, but log 1 is 0, so the return loss is 0 dB. 0 dB means you don't lose anything on the return. What does that mean? That means everything return. That means it's bad if you want to deliver power to the load, because everything is returned back to you, right? Which is undesired. Okay. All right. Again, interview question. Okay. The definition of this are in the cheat sheet, but you should try to do some. Okay. So I want to introduce the concept of stub here and hold on to the examples to later or maybe even next time. Okay. The homework is not due until what, Friday or Saturday, right? Homework, I think.
In your book?
No, my homework, I don't care about that. The other one, waste of your time. It's Friday, right?
Sunday.
Sunday. Okay, good. So you have time. So we can do an example later. Okay. So let's look at stub. Stub is very unique to RF circuit design. What is a stub? A stub is a piece of transmission line that's not connecting to anything. It's like I put a wire in the wall and I'm not going to connect it to anything. It's like, why? Why did you do that? Right? Okay. So if I leave the transmission line open, we call this an open stub. If I would short this transmission line, we call it a short stub. If I connect the transmission line in series, that means they both are on the top line. We call it a series stub because this is short, so this is a series short stub. Okay. name is not that important, but if I just say it in the problem, you need to know what I'm talking about. And if I would connect the transmission line, this piece of transmission line, both to the top and bottom, this is called a shunt. Remember, everything connect to the top line to the bottom line is called a shunt connection. So this is a shunt stub. And because this is short, so I'm going to call this a shunt short stub. All right. So understand what a stub is. It's just transmission line. So why do we care? Because as frequency go higher and higher, the circuit element, especially passive circuit element, is just all about transmission line, right? As frequency go higher and higher, you cannot even buy a cheap capacitor because the capacitor has a resonant, self-resonant frequency. Above a certain frequency, it will not work. So as a cheap inductor, even worse, right? So as frequency go higher and higher, you have no components to buy. Everything you want to make has to be a piece of transmission line. So here are some example of a transmission line design. The white part is the circuit board. That's a PCB. In this case, it's a Lumila. Doesn't matter what it is. It's AL203. It used to be a standard high frequency substrate, PC board material. It's like more like glass, right? So this part, I know it's look dark in color, but actually it's gold. These are gold etching on the substrate. So the input is here, the signal comes in here, connect to this line, and then just stop there, right? If I measure this in DC, everything is open. And then this line is like, it's not even connect to anything. There's no bottom connection, top connection, nothing. It's just like this. And then the signal will go out. So again, if I measure in DC, this is an open circuit, but at some RF frequency, this is a perfect bandpass filter. It's a frequency selective filter. This is another example. This is called edge couple filter if you want, if you care. This is called a hairpin filter because it looks like a hairpin. It doesn't matter. I'm not going to test you that. But this is a very similar design here. The substrate now is one of the Rogers board. Roger has like a few hundred boards. So now you have a lot more choices than a Lumila. So it's the connection going to here. That's a transmission line. Look like a hairpin. That's why I call it a hairpin filter. And they are not connected. There's a gap in between. So it's like a hairpin here, hairpin here, hairpin here, hairpin there. And then it's just going in and out. Again, if you measure DC, this is an open circuit. At some high frequency, this is a perfect pass. And we are going to try to understand how this works and why this works. Okay. On the bottom? Oh, you mean here?
Yeah.
No. No. Just the carrier is bigger than the substrate. No. Here's another example. This is what we refer to in the digital filter. Name doesn't matter. But if you look at the structure, again, we still use a Lumila as a substrate, the white part. The signal goes in here. But look at all these lines, they're all connected. And then these lines are also connected and also shorter to the carrier, shorter to ground. So if I measure DC, this is short circuit. Nothing can go through. Everything will go to the ground. But at some RF frequency, this is a perfect pass. It's a frequency selective, highly selective filter at 20 gigahertz in this case, right? So how does that work? How does a short circuit or open circuit actually works? So all this transmission line, these are called stub. This is a short stub because it's short to ground. These are the open stub because the stub is just left open and not connecting to any devices. This is the magic I want to spend some time with you. Not that I'm going to test you, but I just want to show you how simple RF engineer actually is. If you know what you're doing, your job is really not that difficult. That's why it's such a good career to get into for those who are still shopping. So let's look at this device a little bit. This is called a rat race. Again, the name doesn't matter. Names never matter. This is a 4-port network just because it's 4 line, right? When I say 4-port network, I don't mean this, right? Remember, this is only a 2-port network. When I say 4-port network, I really mean this, right? This is the line, this is the line, this is the line, this is the line, and the other one is the ground at the bottom that we did not see, right? 4-port. Okay, so now depends on how you use it. This is really amazing. The line, all these lines here are just to match the phase. So they are trying to match the exact length, and they're all 50 ohm lines. Right? All this line and 50 ohm lines. The only part of the design is really right here. So what is this? So the line width a little bit different. That's just to match impedance. Let's forget that for now. The distance here, the length here, they are all quarter wave. They're all 90 degree, right? For this half semicircle, 90, 90, 90, then that means the other side is 220, right? You design the diameter such that the whole thing is, is this. 90 degree, not geometric 90 degree. I don't mean this 90 degree. I mean the electrical length. That means this is quarter wave, right? So I know the frequency, I know the wavelength, I divide it by 4, and I just bend that quarter wave into this distance, right? Okay. So now, depends on how I use this 4-port device. Forget about this for now, because that's already fixed how I use it. So let's say if I'm sending away from here. This is my input, right? Then the wave can go, let's say, can go to this port, yes? By 2 different routes. One is taking this route, the other one is taking the longer route, right? From here to here, this signal would have a 90 degree phase shift, the first path. Are you following me? The second path from here to here, what is the phase shift? Also 90, right? Because it's 360 and then 90, that means it's also 90, right? That means these two are in phase, correct? That means I have a signal coming out here, right? So as this side. But what about the 4th link? What about here? Do I get anything here? So when the signal go through here, what is the phase? 180, correct? What about when this go around here? What's the phase? 0 or 360. That means these two are 180 degree out of phase. What does that mean when we have 180 degree out of phase? Complete cancellation. Nothing will go through here, right? So my input power are equally spread into only 2 ports. That is a perfect power splitter. Are you with me? Huh?
Why add the 4th port? You don't want anything going through there. Like, what would you want that to do?
So the question is, well, if you're not using that port, what do you do? Remember when I say if you go to an RF lab, any open, any not unused connector, what do you do? Terminate it with a 50 ohm. So even though nothing should go through, but in case I have a mismatch, impedance mismatch, and something did go through, I want that to terminate it. I don't want it to come back to my ring. to my rat race. Right? Any questions?
Wait, this is a. Slitter?
Yeah, well, depends on how you use it. Yeah, I'll continue. I'm not done yet. There's so many things to learn from this simple design. Can you believe it? This could be your design. It could be, hey, can you design a rat race for me? You know, and wow, that should be easy. Just a ring. You know, how difficult can it be? Right? It's really not that difficult. But you need to know what you're doing. All right. So to answer the question, if you look at this, I can talk about this later, but if you look at this dark thing, this little substrate has a resistive layer at the bottom. So it looks like this. You have a substrate, which is your alumina in this case. The bottom is a layer of gold, which is ground plane. And then on top, you have a trace. But before the trace, you have a layer of resistive material, very thin film. I call resistance. And then on top, you have a gold layer, right? Because it's so thin, it's not very highly resistive. But if I etch off the gold here, the signal is traveling here, has nowhere to go, but has to go through this resistance, right? So that is corresponding to a series resistance here. So this dark thing is your 50 ohm resistor. I will come back to this point later. Very interesting point. Okay. And that's how you make a easy 50 ohm resistor instead of soldering one on top, right? It has a certain advantage, costs a little bit more, but has an advantage. And this part is just for testing, you know, to test whether this spacing, this etching, because it's chemical etching. So if you etch it too long, the gap open too wide, and you have too much resistance. If you etch it not enough, then it's too low of resistance. So this is for you to test the DC probe, right? So anyway. All right, so that's one way to use it. The other way to use it is, I want to say, if I don't worry about power for now, I know it doesn't really, people doesn't really use this way to do what I'm describing. But let's say if I don't worry about power, I'm sending a wave here, right? And then the wave would go into here with a 90-degree phase shift relative to mine, to the input, right? We talk about that. And then, but what about to this line? This is 180-degree phase shift, right? With respect to the input. So that means I get two output. Power would be the same, except I have a 90-degree phase shift, right? I can create a circuit that provide me with the exact same signal at any time, but with a 90-degree phase shift. When do you think you will use it? There are a lot of systems require that. But one thing that related to what we have talked about is to create a circular polarization. How do we create a circular polarization? Tell me, what's the condition? Same magnitude, 90-degree phase shift, and 90-degree spatially. That means perpendicular. This part we can do because we can route it any way we want, right? 90-degree. But same magnitude at any time with a 90-degree phase shift, this satisfies it. Now, if I route this input to antenna that has a 90-degree input to it, now physically it's 90-degree, phase is 90-degree, right? And they have the same amplitude, then the wave that come out from here is going to be a circular polarization. Yeah.
What stops that input from going clockwise back to the second output and then canceling it because it's going to be 360 and 180.
Come back to,
Like if that if
To
it
the
keeps
input?
going, like if it keeps going past that first one, then it adds another 270, right? No, to the second output.
you mean this one,
No, the one where you drew out to.
this one,
No,
this one?
yeah. Like it starts at the input and it goes around clockwise.
Yeah, like I say, there's something missing that I have not talked about. People don't use it to create the circuit price session. They're much better circuit for it. But if you can bypass that, there are ways to bypass it too. You can use it right differently. Let me give you one common use of this rat race. I can use it as a summer. I'm summing up 2 power. Right? So let's look at it. When this come in here, 90-degree phase shift. Come in here, 90-degree phase shift. So these two are in phase. I'm adding them up. Right? So if I call this power 1, power 2, then coming down here is P1 plus P2. Right? But what about going up? This is 90-degree. And this one is 180-degree. No, 270. Right? So these two are 180-degree phase difference. That means they're subtracting. So a simple circuit, I can use it for addition on one side. I have a subtraction on the other side. Right? I can do a simple math here. Are you with me? Okay. But that's not the amazing part of this structure. I'm just saying it's such a simple design that you can make a living, decent living on. Is a good deal. But the amazing part of this example is this following. Remember all the problems we have. We say we have a transmission line. If I don't want to use it, I want to terminate it with a 50 ohm resistor. Right? Where is the resistor? Going from the top to the bottom. So connect this point to the bottom of the substrate. How are you going to do that? Well, you say, well, I can drill a hole called V hole, right? But at high frequency, a V hole has parasitic, is an inductor by itself. Right? So it changed the characteristics of the circuit. So it's not ideal. So one way to bypass that is don't put the resistor through the hole because that's asking for trouble. I'm going to put it on top. So I'm going to put a 50 ohm resistor on top and then just short it. That would be the same circuit, right? Right? Except, wait a minute, I still need to drill a V hole through a glassy material and hoping that it won't crack or micro crack that will crack over time, right? So that's not a good solution either. But then you say, well, then what do you do? Then if you remember what we talked about last time, what did we talk about last time with open and short? Quarter wave. If I want a short circuit here and I don't want to make a short circuit physically, I can make an open circuit. Leave this with quarter wave. So I don't have to drill the glass and risking liability issue of breaking the glass. I still have a short circuit here. And this is what this part is. I'm going to move up a little bit. So this is a 50 ohm line, the transmission line. This is your 50 ohm resistor in series. This is really a quarter wave, but we shape it for other reasons. We shape it to increase the bandwidth reason, but this is really quarter wave here. Do you understand that? Okay. This is why one of the reasons why quarter wave is so useful. You can have a short circuit without shorting it. You can have an open circuit without really opening it. Right? Any question? And if like I say, this is not, looking at the structure, it's not difficult to design. But on top of it, there's software to help you. So it's really not a tough design, but it's a really useful circuit. But it requires you to understand some basic principle of RF circuit, right? Quarter wave, stop. All right, let me give you one more example. Waveguide French. Did we talk about it?
No.
Okay. So waveguide, again, what is a waveguide? It's an empty piece of metal like this. This is a waveguide. This is empty and all the way is empty. When you connect two waveguides together or your waveguide to your housing or your system, you require some screws and fastener, right? You need to bolt them together. So you need to have a flange. So this is called the waveguide flange. Just the lips of the metal that will allow you to put screws through to secure, right? That's not important. What I want to draw your attention to is this groove. Use this waveguide has a groove in it. Now there are two different types of groove that you can buy at the waveguide flanges. Some of them is just to put an O-ring there, right? Just to seal the air to go in and out. But that's not what this is. If you look at the sideway, this is the waveguide flange. The groove that we're looking at is right here. And then this part actually sit a little bit below the edges. So when I put the other waveguide flange here, it opened up a gap. Do you follow my the drawing? Do you understand my drawing? Okay. And so now, what do this do for us? Why do we care, right? Okay. So let me give you some real-time design issues. Let's say when we use waveguide, usually it's because we want to deal with high power, like kilowatt of power, right? And so you need to put the two waveguides together, and then you put them together like this. Okay. And here, ideally, because they are the same size, ideally, this connection is like very smooth, right? Because you can buy and make this waveguide to very high degree of accuracy. But how high? 1/1000th of an inch, is that high enough? That's 1 mil, right? Is that high enough? Right? And also, even if they are exact, when you put these two pieces together, do they align them exactly? Because there are some place, there's some clearance, right? So you can put the screws in. If everything is so tight, you cannot even put the screws in. Has to have some room to play. So now, in reality, the size is not exactly the same size. It can be off by very little bit, 0.5 mil, 0.00005 inches. That's very small, right? Then you're looking at a structure more like this. I exaggerated, right? But what does that mean? What does that do? When I have kilowatts of power going in, seeing a sharp corner here, what is that going to do? Zap, arcing, right? We call it corona, which is, dielectric breakdown corona effect, not the drinking corona, right? Corona effect. It will burn your devices, okay? And you cannot avoid it. So how do we get around this problem? By not connecting them at all. Open it up a gap. How would that help? That comes the magic quarter wave. So here at the bottom of the groove is metal, so it's short. This is quarter wave, so this appears to be open, right? This is open, the distance to here is also quarter wave. So here at this point, it appears to be short. Even though this is not physically short, but for the RF, for the electromagnetic wave, oh, that's short, it just goes through. It's short. You can handle a lot more power by opening up a quarter wave gap. Right? That's amazing. No, you don't find that amazing. You don't find that interesting. I find that very amazing. So, and if you're lucky, you will get an assignment, as to design this groove. Again, there's software to help you, but you need to understand the concept before you apply to the software, right? Right. So most of the groove, the waveguide, you can purchase it. So if they can buy it online, they're not gonna have you design it because you are expensive. How much you say you want? I don't forget, right? You're expensive. So, but there are cases where like I want the connection to be on my box, and I don't want it to have the solder and do anything. So that's the time that you ask an engineer to design this grooving in your connection, right? Out of decades of me in the industry, I only did that once, but it did happen. Okay. Any questions? That is a range of frequency, but you have to optimize it. Yeah. If you're making it custom made, of course you optimize your frequency.
Can you explain?
Fun job, huh?
Can you explain that? So it sees a short from that first quarter wave.
Yeah.
And then it sees open from the second quarter wave.
So quarter wave of short, this is short. That means at this point, it's open. This is quarter wave, right? This is transmission line. So quarter wave after the short is open. And here is also quarter wave, open after quarter wave, this becomes short. RF wave, right? As far as the electromagnetic wave see it, it sees a short.
Across the two flanges.
Yes, across these flanges. So you see a short in here. So nothing to leak, go through. Two examples I show you, I thought is especially this 50 ohms, not really making a physical short, but it is short. This is amazing. This part is worth thinking about it. And again, if you look at both design, they're not difficult. They're not complicated, right? That's why I keep encourage you guys to look into RF engineer. The job is good, you have more job opening than career. Everybody needs it, even Intel needs it, even Cisco needs it, right? I mean, anyone needs an RF engineer these days.
What is square?
Huh?
What's square?
This 2 square, that's to check the etching. Right? So if you etch it too long, this square becomes open. The resistor is also to test the resistance. Yeah. This is, a lot of people put that, just to test how good this etching is. If we etch over time or. Yeah. So let's go to more stuff. Yeah. So this one is a low pass filter. So the inputs, the signals coming in here go through transmission line with different impedance, and then go out. What I want you to pay attention is this 2 line. There's a line sticking out here. It's not connecting to anything. But you need that. Right? So why are they there? What do they do? That's stuff. If you don't understand stuff, you don't understand anything about RF design. Stuff. So let's look at two special cases. The first one is short stub, right? Short stub, that means I'm leaving this, shorting this end. A stub, what is a stub again? It's a piece of transmission line. So I'm going to start with my transmission line formula, right? And then this is my transmission line formula. It works for all transmission line. Now, if I have a short stub, that means my low impedance is 0, right? That means this is short, so this is 0. So if my low impedance is 0, then my impedance is just J times tangent beta L. This is normalized impedance. That means if I unnormalize it, a short stub should be J Z naught tangent beta L, and this Z naught is the characteristics impedance of my stub impedance. There's so many transmission lines in the circuit. You need to know which circuit you're talking about, right? All right, so now what does that tell me? My impedance is a pure imaginary number. What components would you think of if you're thinking of a pure imaginary number? Inductor. Because the inductance is J omega L, purely imaginary and positive, right? So that means if I have a piece of transmission line, it looks like an inductor. But wait a minute, this is a tangent curve. Tangent curve is a periodic function, right? So that means if beta L, the line length or the frequency, if the frequency is low or the line length is short, a piece of short stub behave like a series inductor. But if it go over pi over 2, quarter wave, now it's a negative. Negative means what? Now it means it behaves more like a capacitor, because capacitor has a purely imaginary but negative impedance. So at any frequency, at any point, let's say I need this inductance, that means this impedance, I can always simulate that with one piece of short stub. And in between, when this is equal to pi, the line length is equal to pi, which is lambda over 2. This becomes a series resonator because the impedance in that case is J omega minus 1 over J omega CLC, and then you know, pull the common factor and you can write it this way. And omega's, this is the resonant frequency, omega squared is equal to 1 over LC, and when that is at resonant frequency, when it's at this point, this is equal to 1, 1 minus 1 is 0, my impedance is 0. Right? If the frequency is higher than that, this becomes positive. It behaves like an inductor. If the frequency is below that, it behaves like a capacitor. And if this line length is quarter wave, now it behaves like a 10 circuit. Still a resonating circuit, but the impedance is different. The impedance is given by this. At the resonant frequency, omega squared is equal to 1 over LC. This is equal to 1, 1 minus 1 is 0. That becomes infinity. And that's why at that frequency, my impedance is undefined, right? So you see, it depends on how you use a short stub. You can use it as an inductor. You can use it as a capacitor. You can use it as a 10 circuit. You can use it as a series resonator. And that's what we use in the earlier example I show you. Let me give you an example. So short stub, quarter wave is 10 circuit, right? How many of you have you learned network? I mean, like electrical network. You all have some, right? Like what is a high pass filter? What is a low pass filter? Oh, okay. So now look at this again. Right? We look at this example. This short stub. Remember, we say quarter wave short stub is a 10 circuit. Yeah. And then I have a number of them. In between, I have a line, a very thin line is like an inductor. So my circuit, it looks like this. For those who understand network, what does that look like? This is a coupling, a couple frequency selector coupled with this. That's a bandpass filter structure. That's why this is a bandpass filter. At what frequency? At the resonant frequency of this. Because at resonant frequency, this is infinity, undefined, so nothing, the signal go in here cannot drain to the ground. The only way it has to go is go through. That's why at that frequency is a perfect pass. Because at that frequency, all this becomes infinity. Right? Easy enough to understand? All right, so I still owe you some examples, which we will do next time and hopefully make things easier. But in the meantime, please start doing your exercise. Only 20, 30 problems you need to do, right? Start doing it. We're running out of time.
Can you scroll down? To the tangent graph showing the different components.
Oh, you want that graph?
I want to, what's the knob that you're turning on? Is it the length of each stub? Is that what you're changing? Like,
The length. Well, so if beta L, we plot against beta L.
yeah, but of those things, the knob you're turning in your design is generally L, right? Like you're changing the length of your stub to change what the wavelength.
Yes. So even if I want an inductor, for every inductor, let's say you calculate J omega L, that's your impedance that you want. You say, I want this impedance. So that means that's the length I want for that frequency.
For that frequency.
Yes.
我是我们看到的ID
Because I was talking to Wyatt, and he started showing me some like advanced stuff. And he said, wow, why?